G'day, in this video we're going to be focusing on generators and looking at the DC and AC versions of them. Our syllabus content today is going to cover 6.4.2, we're looking at Module 6 Electromagnetism, and Inquiry Question 4, which is looking at applying the motor effect to technological advances. Technically, even though the inquiry question doesn't cover it, we're also looking at the application of induction. And induction is what's required for a generator to work. So we're going to be analyzing the operation of simple AC and DC generators. In a future video, we'll look at AC induction motors. So our key learning intentions today, first we're going to use a right-hand rule to predict the direction of induced current. We're going to compare energy transformations in motors and generators, and then we're going to look at AC and DC generators, how they're similar, how they're different. So first off, when we're looking at determining the direction of current that is running through wires that are undergoing induction, we can apply Fleming's right-hand rule. Previously, we've looked at this in terms of Lenz's law and Faraday's law, where we treat a wire as essentially a charged particle moving through a magnetic field. When we apply Lenz's law, the idea here is that the direction of the electric current which we induce is such that the magnetic field which is created opposes the change in the magnetic field, or in this case, opposes the direction of motion of the wire itself. Effectively, what we have here is that the maintenance of the law of conservation of energy, ensuring that we don't create perpetual motion machines. So using Fleming's right-hand rule for induction, we should see that we work with the same three vectors. We've got velocity, we've got a magnetic field, and we've got force. Velocity here is referring to the direction that the wire is actually moving. So for a generator, we're talking about the direction that it's rotating in. We've got our magnetic field that the generator is sitting in. And then we have this force here, which essentially is the electromotive force, and that pertains to the direction of current. This vector always comes out of our palm. So when comparing motors and generators, first I want to look at these right-hand rules that we have over here. You may see versions of the right-hand rule which are about the palm rule. So we have the right-hand rule for the motor effect and the right-hand rule for induction. But that can also be shown using the three-finger version of the rule. It really doesn't matter what strategy you actually use to determine the direction of all vectors for either the motor effect and for induction. As long as you are confident with that system and you can consistently make correct predictions about the direction of these vectors, it really doesn't matter which one you pick. For motors and generators themselves, they really do very similar things, but in very opposite ways. Motors start with electrical energy supplied by some sort of power source and convert it into kinetic energy, rotational motion in the coil, and thus the axle, which can then be used for many, many different applications. Generators, on the other hand, start with kinetic energy and convert that kinetic energy into electrical energy. They're built extremely similarly. There's a coil of wire which rotates around a magnetic field. And fundamentally, the only difference is whether or not you start with kinetic energy and generate electrical energy, generate a current for later use, or you're using electrical energy to convert into kinetic. And this base generator concept explains how we generate most of the electricity in everyday life. Really, apart from solar panels, every other type of generator relies on the induction concept that we've been talking about already. And in order for this to occur, you need to have some sort of conductor spinning around on an axle surrounded by a magnetic field. This action will lead to the generation of electricity. So the question becomes, how do you make something turn over and over and over again? How do you make this coil turn, have induction happen, and generate electricity as a result? So for many of these scenarios, we find some sort of fuel source which we're able to burn to heat up water, create steam, and have that moving steam turn a turbine, essentially an axle, with a conductor on it, which is then able to interact with the magnetic field which surrounds it and generate electricity. So things like fossil fuels, geothermal sources, hydrogen fuels, as well as nuclear fuels can all be used to boil water. These boilers push steam through your turbine and get that rotation happening. However, there are some other ways too. In particular, wind and hydro, two fantastic renewable sources. Wind, obviously, you get some fan blades that spin in the wind, that turning of the turbine generates electricity. We also have hydro. We can take advantage of consistent sources of flowing water and allow that flowing water as it's passing, say, down a mountain or a hill, to be able to turn the turbine as it goes. People have actually been using hydro energy for a really long time. Think, say, a water mill, which might be used to grind or mill wheat. Similarly, windmills have been used well before electrical generation as well. So when we have a generator, the general concept is we have a coil of wire, it rotates around, that rotation is causing induction, and the induction within the loop is connected to a larger circuit, which can then be powered by that generator. However, sometimes generators are set so that there is direct current. Sometimes we have an AC generator instead. The major difference between the DC and AC generators are the rings which are used to connect the armature, the loop, to the external circuit. In the case of an AC generator, we have slip rings which maintain a permanent connection between one side of the armature. So if we look at this diagram over here, what's essentially going to happen is that the coil is going to be free to spin. And in the case of this side of the loop, it's always going to be in contact with this slip ring. It won't be in contact on the other side though. Instead, this wire will connect to the slip ring at the back. And essentially what you have here is that the loop is permanently connected to one of the slip rings at a time. This will generate AC, as with every half turn, the direction of induced current is going to flip. Our trusty commutator comes back for our DC generators. Essentially every half turn, the commutator is going to change which side of the external circuit the loop is connected to. And thus, every time we have a half turn and the current flips, it's not going to change the direction of current for either terminal that's connected to the external circuit. Similarly to how the commutator for a DC motor works, where you ensure that your connection to the external circuit supplying electrical energy flips, ensuring that torque is always in the same direction. So a little bit of another diagram for a DC generator. Again, you've got this commutator which is flipping the direction of current. So again, you've got this commutator which is accounting for the fact that every half turn is going to lead to a flip in the direction of the current. This is going to maintain an EMF in the same direction around the external circuit permanently. However, what you will get is areas of peak EMF and areas of zero EMF. Peak EMF is going to occur when the loop, in a sense, it's parallel to the magnetic field. However, you're going to end up with zero EMF when you've got the loop sort of perpendicular to the way that it is now every quarter turn. For our AC generators, again, we have slip rings where each of the two slip rings is connected to one side of the loop. The slip ring ensures that the armature, or the particular side of the armature, is permanently connected to that slip ring. What that's going to mean is as you go through a full 360 degree rotation, you're going to experience areas where there is maximum EMF in one direction, maximum EMF in the opposite direction once you get to that half turn. And when you get back to that full 360 degree turn, you will then have maximum EMF back in the original position. And this is simply because you're going through that cycle again where you will have maximum EMF every half turn, but each half turn results in induced current in opposing directions. This here would then lead to AC, alternating current, which is going in both directions. Thank you very much, everyone. In the next video, we're going to look at some other applications of the motor effect and induction. But until then, have a good one.